Hello, in this video we're talking about time dilation, one of the crazy things that happens as a consequence of the rules of relativity. Time is strange, it's funky, it's not the same for everybody, despite our everyday life experiences, so we're going to get into it. All right, we want to use our main rule, and the main rule of relativity is that the speed of light is constant for everybody in an inertial reference frame. That's really what everything boils down to. And all the crazy rules come out of that. So here's a classic example of kind of how to derive this rule, and we won't do all the fun math, but we can look at the idea. So you can talk about something called the light clock, which is a fun way to measure time. So let's picture we got an astronaut on a space shuttle here, and they have this light clock, and the idea is like you have a little thing that shines light, and you have a mirror. So what's going to happen is light's going to come off, go up, hit the mirror, come back down, right? And so the time it takes depends on the distance and the speed of light, which is always the same. So it goes at a certain speed. It takes a certain amount of time to go that distance. And so you measure the time it takes the light to go up and back down. This distance, call it d. All right, that's the time that the astronaut would measure here on the space shuttle, with all of that happening at the same place, right? Okay, now picture somebody on the ground with a telescope looking up at the spaceship, and there's a window or something they can watch the light clock. Okay, the ship is moving side to side, so the path that the light takes will not be straight up and down to this observer, right? The light. So here's the astronaut. The light leaves and hits the mirror. When the light hits the mirror, the spaceship has moved over some distance. So to a person on the ground, the light is going up at an angle, right? The light goes up, hits the top of the mirror when the spaceship is here, and then comes back down to the mirror when the bottom, the sensor, when the spaceship is here. So this is the path traveled by the light to somebody on the ground because it goes up and down, but also side to side with the moving reference frame of the ship. Okay, so with just a right triangle, we can see this is the distance, double D is how far the light goes as measured by the astronaut. But some fun right triangle stuff is how far the light goes to an observer on the ground, which is a further distance. And this observer will see and measure that light to travel a further distance. But remember the rule, it always goes at the same speed. So the thing that's set is that that light goes at the speed of light, no matter who you are. And if it's going at the speed of light to the observer on Earth and it's going a longer distance, it's going to take a longer time. And on the Earth, you will measure that event for the light to go up and reflect back to take physically longer. And that idea is called time dilation. Okay. So we do need sort of a baseline for this. And the baseline we call proper time. This is a part that can get a little confusing. The key thing to remember is if it happens at the same location, that's the quote proper time. It's not the best use of words because it's not to say that the time measured by this observer is wrong. It's not. It's the time they measure in their reference frame. But the way the math works is we have to do it. If you're moving in space as well, it's more complicated. So the event where there's not like motion through space, we call proper time. So we're going to call the time measured by the astronaut proper time because event A is a light leaving the source, event B is a light hitting the receiver, and they're at the same position. So we'll call that the proper time, two things that happen at the same position in some reference frame, right? That those events don't happen at the same position in this observer's reference frame. That's part of the key idea. And so if you measure from a reference frame, any other reference frame that's moving relative to the frame in which you have your proper time, you measure a longer time, just like here, because of this reason, because it's moving further. The light has to move further. And so this is called time dilation because the time is longer and it's physically measured to be longer. Okay, so that's sort of the concept. If somebody's moving relative to somebody else, they're going to measure different times for events to happen. So time is not absolute. Okay, so let's get into the equations. Here is the basic equation for time dilation. So we're going to define two things. One is that proper time, we're going to use delta TO. So delta meaning like time between sort of two events, the amount of time that it takes from, light leaves the emitter to light hits the sensor, whatever. This whole thing represents proper time, and this represents the dilated time. So we have some value here that's going to like scale it up. This is sort of your scaling factor. All right, so we have that factor, which is called the Lorentz factor. And this comes up in so many relativity equations. It's a big, big, big part of relativity that accounts for this, like, dilation that will happen, or later fun stuff like contraction of length. All right, and one thing to note when you use this equation, you can use any matching time units because it's really a ratio. Really, this is a ratio of the dilated time to the proper time. You could get both of them in years, get both of them in seconds, whatever. Okay, what's the equation for the Lorentz factor? It's so fun. Boom, there it is. It's in your data booklet. All right, there's some fun Pythagoras happening here, if you can see it. Some fun right triangle stuff that you can kind of derive from that light clock thing if you want to have some fun. But it's given in your data booklet right here. All right, so that's how you figure out this guy. You do all this good stuff. You're going to do this so many times, you're going to get very, 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 very used to this big fun fraction where, okay, you have in the denominator square root of 1 minus the speed between the reference frames. That's the same v we've been like dealing with in all our relativity stuff, and c is the speed of light. The thing is, this v is almost always going to be in terms of c, so it basically turns into a decimal that you square, but we'll look at some examples. All right, but that's the equation for Lorentz factor, which is this. It's the Greek letter gamma. Gamma is what that is. It's not exactly a y. It's Greek letter gamma for Lorentz factor. All right, so those are the equations. So anyway, let's look at how to use them because they're kind of wild. All right, so how do we know that this is a thing? Because it seems crazy to say if something actually happens on a spaceship, somebody on the Earth would measure it to take a different amount of time, but it's true. It's absolutely true. We do measure it. All right, the main piece of evidence that the IB wants you to know about and talk about, because they will likely say, what is our experimental evidence for like time dilation? And it's something called a muon decay experiment. So fun. Okay, so what this is these are subatomic particles. Muons are really, really, really small particles. Cousins of electrons, if you will. All right, they're in the same sort of family. They're really, really, really small. Little subatomic particles, and they're unstable, so they will decay radioactively. So muons will undergo some kind of decay, and the average lifetime is 2.2 microseconds. So that's why you probably haven't heard about these guys so much, because they don't like hang out in our everyday life. They're like flying through the atmosphere from time to time, but for very short amounts of time, because after about 2.2 microseconds, they decay into other stuff. Okay, so you can measure this. You can see, like, this is an average, so you get a bunch of them, and you see on average they take 2.2 microseconds to decay. However, that's like a proper time. If they're moving, and we've done this, we've made muons move really, really fast and measure how long it takes them to decay, and it's way longer, right? You can do the math. In fact, we'll do it in a second. If they're moving this fast, and we can get them this fast, like 99.9% the speed of light, then you can use your little Lorentz factor and figure out that the time it should take relative to lab is more like 63 microseconds. Many, many, many times longer. Yeah, so muons at rest, we measure them to decay on average 2.2 microseconds. Muons moving real fast, we measure the decay to take longer because of this time dilation. All right, so that's the main piece of evidence that you want to know. Some other good and maybe more common ones, atomic clocks, which are like really, really, really super accurate clocks that use crazy things like oscillation of atomic particles to keep really, really accurate time. They show time dilation because you like fly them around the world at some relatively fast speed, and when they're moved, the time gets offset. The time changes, and so we need to account for that and use time dilation. GPS satellites are really similar. GPS satellites are moving relative to the Earth, and so the time is always different. We will always measure a longer time, a dilated time, compared to the GPS satellite. If the GPS satellite measures 1 second, we'll measure that same 1 second to be just a little bit longer because they're moving relative to us. And so they work these calculations into the GPS calculations. It's pretty significant. If you didn't have these time dilation calibrations, the fact that the times do tick at different rates, you would have 10 kilometers per day, your like accuracy of the GPS would be off by something like 6 miles every day. It would start to drift by and you'd be way, way, way wrong in terms of where you're at and where to go. All right. And again, it's because these take different. The similar experiment that we've done is you take two synchronized clocks, you put one on a satellite, keep one on the Earth, you fly the other one back down, and you will see that they have measured different amounts of time. Crazy, crazy. All right, so that's the main evidence you want to be aware of. And let's look at some. Let's do an example of time dilation, a famous, notorious physics problem, the twin paradox, which we're going to do with two twins, Sherry and Terry. Sherry and Terry are having their 10th birthday party, minding their own business, when suddenly one of them, Sherry, is abducted by aliens. And just to make it extra twinny, some twin aliens abduct them, Kang and Kodos there. The alien vessel moves away from the Earth with a relative speed of 0.98 c, so 98% the speed of light. It goes 5 years, then turns around and comes back to Earth. So I'm thinking it goes 5 years out, 5 years back, making it 10 years, right? So Sherry is 20 now, after her 10 years in the spaceship abducted by aliens. The question is weird. How old is Terry? Well, surely 20, right? They're twins. Same age, no? I think no, because relativity is crazy. Here's the deal. I have two moving reference frames, two people in different reference frames measuring times. They're going to measure different amounts of time. That's what we said, weird as it is. Because there's a very fast speed between the two reference frames of 0.98 c. Yeah, 98% of the speed of light. So we're definitely going to see some relativity. Let's see how much. Well, I want to get two different times, so what I want to do is definitely use my time dilation equation. Delta t equals gamma, the Lorentz factor, times delta TO, the proper time. Now, here's what we got to think about is like, what is the proper time and who's where? So, okay, Sherry is on the spaceship that goes like there and back, yeah? The way we're going to do it is the 5 years, so this is in terms of the ship, right? So that 10 years passes inside of the ship like to Sherry, yeah? So 10 years goes by because in the reference frame of the ship, Sherry's just grown up, Sherry's hanging out in the same place, 10 years go by. That would make this, since it's measured relative to the ship, even though we might think the ship is moving, this is the proper time, 10 years, okay? Because 10 years happens at the same place in the reference frame of the ship, and we're saying 10 years goes by for Sherry. So that's the proper time. Sherry experiences 10 years of time. We'll call that the proper time. Now what we got to do is figure out gamma, the Lorentz factor, which we're going to use this fun equation of 1 over square root of 1 minus v squared over c squared. All right, so we just plug in the numbers we got where v is 0.98 c. So we're going to get some cancely stuff, and this is just going to become a decimal, and you're going to get very used to this, doing this all the time. So let's write it all the way out. We got 0.98 c, and I got to square the whole thing, right? I'm squaring that whole v, and divide by c squared. All right, well, the way math works is the c squareds are going to cancel out, right? Because I square each thing in the parentheses, so c squared, c squared. I do still have to square that 0.98 though, yes, because it's in parentheses, I'm squaring the whole v. So what I end up with, and it's pretty much always going to look like this when you do your Lorentz factor, is 1 over the square root of 1 minus 0.98 squared. Oh, fun. Yeah, so some fun for your calculator there. Make sure you can do it. Make sure you have some calculator skills. Don't mess up your order of operations. Slap some parentheses around there to make sure you're good. And if you do it right, you should get about 5. 5.025 is the Lorentz factor, the factor by which time is dilated. Whoa, so if I go to this equation, then delta t, the dilated time from Terry's perspective, this is, remember, Sherry's perspective, is going to be delta t gamma of 5.025 times the proper time of 10 years. Holy moly, I got 50.25 years have gone by for poor Terry sitting here on the earth waiting for her sister. So by the time 20-year-old Sherry comes back, she's going to meet a 60-year-old Terry. Yeah, and that's the twin paradox. It's real. We have not done this experiment with twins, to my knowledge, but with clocks all the time. You put take two clocks, keep one on the Earth, but one like we said, in a satellite. The clock on the satellite does not tick as much as the clock on the ground because the time is dilated for the person, for the clock on the ground, essentially. All right, so the same math as this. So it really does and would happen if you have a twin and they go flying away really, really fast for a long time. They'll come back and you won't be the same age because physically the time that passes is different because of relativity. Time relativity is bananas. All right, so there's the twin paradox. Let's do one more. Okay, one other example. We can use that muon decay example, which is a good one to know because, again, that's the main evidence we have. We've really done this experiment and really see this. Okay, so those are the muons, the subatomic particles. They decay with an average lifetime of 2.2 microseconds when measured at rest in a lab. If a muon is produced with a speed of this much relative to lab clocks, estimate how far the particle will travel before decaying. That's fun. So we're trying to find some kind of like distance. Okay. Again, I'm given time and a speed. So based on what I have, I'm thinking I can do that time dilation first. And probably use some kind of time dilation to figure this out. All right, the first part, though, I don't even really have to deal with that because classical physics means like pre-relativity stuff where you can use, if you see this, it's a clue to just use basic Galilean, Newtonian stuff. And this first part is real easy. All we do is we say, okay, well, it's going at a constant speed of this fast for this long, so I'm just going to multiply them. I'm going to do distance equals rate times time, basically, right? Suvat when a equals 0. So all I do is I say the distance is 0.9994 times the speed of light, so times 3 times 10 to the 8 meters per second. Yeah, and I'm just going to multiply that by 2.2 microseconds, which is 2.2 times 10 to the minus 6 is what micro means. The front of my data booklet will help me out if I don't know that at this point. And multiply all this together, right? I'm going to get my answer in meters, just multiplying speed by time to figure out how far it goes. Put this all in your calculator, multiply it out, you get like 659.6. Let's go to sig fig because of this guy. So 660 meters is how far this thing should go, right? Because it'll take 2.2 microseconds to decay. It's going, almost 300 million meters every second. And so it'll go this far in that 2.2 microseconds. It should. But according to special relativity, the distance that it will travel in the lab is going to be different because it takes a different amount of time. So how long does it take? Okay. We have two frames here that we're dealing with. The first frame is the lab frame, which would be, we would call it S or something like that. The second frame is the frame of the muon. You can picture like a coordinate plane attached to the muon, where the muon is the origin. And the lab is like whizzing backwards past it, if you want to picture it that way. All right, so we have the lab frame and the muon frame. Think about this. Which one is the proper time? That 2.2 microseconds, is that the proper time or the dilated time? Okay, I would say that is the proper time because this is one key, is measured at rest in the lab. And also that's the time that it would take in the frame of the muon, because to the muon, it does take 2.2 microseconds for it to decay on average. But that 2.2 microseconds for the muon is a different amount of time for somebody in the lab if the muon is moving real fast. How much longer? Let's use the time dilation equation. So I do gamma times my proper time, and I'm going to find the gamma. Yeah, so gamma is going to be my Lorentz factor 1 over 1 minus, square root of 1 over 1 minus v squared over c squared. Let's do this, 0.999 94c squared over c squared. So same deal, the c squareds will cancel out. That's going to become 1 over square root of 1 minus 0.9994 squared. All right, punch that all in your calculator, and you will get something like 28.87. Okay, we'll round it there. Okay, that's my Lorentz factor. And if I multiply that by the 2.2 microseconds, this is where we get that number from, 28.87 times 2.2 microseconds. So I plug it in here. So let's take this and put it in here. Oop. And delta t0 is my proper time. So this is going to become 28.87 times the 2.2 microseconds. So I get 63.514 microseconds. Okay, and that is this number that we measured. Yeah, that's like the evidence. We actually do measure that to happen. So while the muon experiences 2.2 microseconds of time and then decays, the lab measures it takes, in the lab, you measure that muon hangs out for 63 microseconds and then decays. Crazy, time is relative. Okay, so that's how long it takes. Now we can use this same idea, because now if we're in the reference frame of the lab, I have a thing that hangs around for this long and is traveling this fast. So I can now just use distance equals rate times time now that I have my dilated time. That's the relativity part. So I can just use now 0.9, just like I did before, 9994 times the speed of light, 3 times 10 to the 8. That's meters per second. And then I multiply all that by the time that it really moves through the lab for this many microseconds. There you go. You multiply that through and we get ourselves like 19,042.76, yada yada, all around to 2 sig figs. So like 19,000 meters. 19 kilometers is how far it goes. And again, is measured to go in like a particle accelerator, these big gigantic things. Yeah, so very different. And if you divide those, it should be about 28, 29 times bigger, and it is. You multiply that by 28 or 29, you get this. All right, so that's the idea. The Lorentz factor scales it up because it takes a physically longer time in the laboratory compared to its own reference frame. The times are physically different and are measured to be different. All right, so there you go. Time is relative. Even more fun to come when we start talking about things like length and some other places that this gamma factor comes up. But there you go. There's your first taste of some real relativity. So go think about that. Think about your twin paradox and all that fun stuff. It is very fun, and it's only going to get more fun. So I'll see you then.